Okay, welcome back again. Today we will see some examples on a circular channel. So a circular channel is a closed conduit in which the fluid is not subjected to atmospheric pressure. Rather, it is just subjected to hydraulic pressure inside the pipe. So the pipe may just may have full or partial. So it depends upon the fluid magnitude. So you can see this arrangement. This is just a circular channel. If it is a center here, for example, if the center is around here, so the water surface may be above the center of the circular channel or below the center of the circular channel. So it depends upon this depth y, this depth y. So you have here center, then this is the angle subtended by the chord of the water surface. So you have here theta, 2 theta is the central angle. So sometimes it may be below. So if it is below the water surface, so the angle subtended by the water surface will be at this point. This is 2 theta, which is the angle. So y is smaller than r. Y is smaller than r. But here y is larger than r. So we will have some calculation step. So a pipe may be full or partial. So for example, let us see for full flow. For full flow, hydraulic radius, you can see A over P. So A over P means area is pi over 4 d square. And perimeter or circumference of the channel is pi times d. So if you cancel d, here cancel d1, then pi cancel. So this is d over 4. So for a pipe which is flowing full, the hydraulic radius is 1/4 of the diameter. Then if you substitute this in hydraulic radius in Manning equation, you will find this equation. So this is the general equation for discharge which is flowing full, especially in water supply distribution system, in irrigation pipe system, etc. We require a pipe full, and also in turbine, in penstock, it is just required to make full, so that the pressure is just allowing, and then it will run some engine or motor or etc. So I think once we have this, sometimes we have some chart or table, standard table. We can see. Let us see this one. Let us see this one. You have such type of chart. So for example, if you have part divided by full, ratio of proportion of partially with respect to full, and velocity with respect to full for circular channel, you have such graph, which is the dotted line is for velocity, and this is for discharge partial with respect to full. So if you compute the ratio of partial with respect to full, either velocity or discharge proportion, then you can just take this one. So if you get the velocity, then finally this point, it will go at this point, which is y over d. So once you get y over d, since d is given, the diameter of the circular conduit is known, you can find the partial depth of the circular channel. For discharge again, you can just calculate here. This one, you can go at this point. So for a single point, either V or discharge proportion, you can find Y over D. And this is just a table, which is variation of Q with respect to Q full or V full in circular channel, factors of for a pipe. Part to full, partially to full will be this one, proportion of depth given, velocity proportion given, then proportion of discharge, etc. given. Then you can interpolate, and then you can arrive the depths at which the discharge is going, either full or partial. So let us go to the example now. A circular channel 2.5 meter in diameter is made of concrete, Manning roughness 0.014, and is laid at a slope of this one. So the gradient is given. Calculate the discharge if the depth is 1.5 meter. If the discharge is unknown, but depth is known, if normal depth is 1.5, what will be the discharge? So answer is here. Calculate the depth of flow for a discharge of 15 meter cube per second. So we get this one. Let us see the solution step by step. So once you have this y with respect to the ratio 1.5 to 2.5, you have 0.6. So you can read table from RK subharmonic flow in open channel. Then we can arrive at the solution because already we know this equation Qn over radical S naught d to the power of 8 over 3 equal to this one, 2 theta minus sine 2 theta the whole 5 over 3 over 32 theta, the power of 2 over 3. So theta may be difficult to iterate. To iterate like trapezoidal channel, we just solve n naught, then finally we arrive normal leaves, but for this problem, it may be difficult. But AR 2/3 over d to the power of 8 over 3 is this one. So you have this for 0.6 ratio, we have this one. Then if we just crisscross the unknown values, this one, only discharge is unknown, for a depth is given, then finally y over d already 0.6, then you have this one, then crisscross, then finally the discharge will be this one. So you can read out from table 2A1 from subharmonic, you can have this table. This is a table. You can read out from this table. This is just for circular channel and trapezoidal channel table. You can just use this table. So for 0.6 for this one, 0.6 y over d ratio, what will be AR 2/3 over d to the power of 8 over 3. You have here. And this is for section factor. For critical depths, we will use this one. But for normal depths, we just follow this one. AR 2/3, then finally this one, then crisscross, then finally we can compute the discharge. So once you have discharge, then for a discharge again, for a discharge 15 meter cube per second, what will happen? So the angle subtended by the water surface, by the chord of the water surface, since the depth is larger than the radius because the radius is 1.25, so it is above the center point. So you can have this angle, which is the angle subtended by the water surface. So 2 cos inverse of 1 minus 2y over d f of yd. Then you can find 2 theta from table again. You can read out. Otherwise, you can calculate using this equation radian measure. You have to convert into degree measure. So for a discharge of 15 meter cube per second, you simply Qn over radical S naught d to the power of 8 over 3 AR 2/3 over d to the power of 8 over 3. Again, we compute this one. Then read out from table y over d. You read this. How do you read? Let us see again from table. From table, just from table, this one. 0.256 something around here. So it is between this one. Then you have this one. So you can interpolate. Then the central angle also you can interpolate. Clear? The angle subtended by the water surface. If discharge is changing into 15 meter cube per second, you can find the angle subtended by the water surface, area of the channel, perimeter, top width, etc. You can compute automatically from table. So y will be this one. Just crisscross. After you interpolate this one from table, then we get this is the depth for this one. You see, if discharge is reducing, then the depth is increasing. So I think you can just calculate. Again, let us see now compound channel. For the compound channel shown below, determine the discharge for the depth of the flow y 1.2. Total depth of the compound channel is 1.2 using partial area method and whole section method. So take n naught 0.02 and s naught 0.002. So you have answer Q partial, this one. Then let us see this calculation. So you have total water surface width at the top 17 meter and left and right. You have portion 1, portion 2, portion 3. Clear? So we will calculate each area. So using partial area method and whole section method, what will happen? Let us see the calculation. So you have 0.9, the deep portion depth of this channel, the main central portion, but the remaining will be 0.3 because you have 1.2 total depth of flow. So you have here 0.3 meter, 0.3 meter depth of water, Here 0.3 given. Then let us see the solution step by step. Using partial area method for sub area 1 and 3, they are symmetric, equal. So 7 meter, you have 7 meter width, then 0.3 meter, like this, So you have 0.3, which is this one, 0.3, this is 7. So on both sides the same. So you have to divide. Vertical interface method we can apply. So P1 again, you have 0.3 plus 7, only the boundary of the channel. This should not be included. So 7.3 and R1, A1 over P1, you have here. Then discharge should be computed for this region and for this region. They are equal. So 1 over n, then area you have A1, then R2 third is the power of half. So you get 0.648 meter cube per second for this region and for this region. For the central portion, let us calculate now. For the sub area 2, which is this one, for the second area, 3 meter by 1.2, because you have 3 meter. So area should be calculated all region, which is 3.6 meter square. But when you come to perimeter, you should only include the boundary of the channel. So this is 0.9. So you have to consider only this boundary of the channel. 0.9 plus 0.9 on both sides, then plus 3, 4.8 meter. Then R2 will be A2 over P2. You have 0.75. Then calculate Q using Manning equation. 1 over n, area A over n, R2 third, S to the power of half, you get 2.1 meter cube per second. So total discharge will be the sum of all sub areas according to partial area method. You sum up, then you get 3.396 meter cube per second. Okay, let us see the second method, which is total section method. For total section method, you simply sum up total area, 7.8 meters square, P again, total, P1, P2, P3, then finally you get this result. R, area over weighted perimeter, you have this one. Then discharge according to the whole section method, since Manning roughness is the same for all, otherwise you have to compute an equivalent here. So it will be 3 meter cube per second. So it differs from the first calculation. QP partial discharge is greater than whole section method. So why this happens? Because we consider each roughness, each area, and each weighted perimeter and hydraulic radius for each cross section. But here we just take the overall area, perimeter, R, etc. Then that's why it declines. But for that case, each roughness should be taken into account. That's why partial discharge is more than whole section method. Okay, composite section method. If you have different roughness, you have to compute Manning roughness equivalent Manning roughness. A rectangular channel has a bed width of 2 meter, depth of 3 meter, and laid at a slope of this bed slope. The channel has a coefficient of roughness 0.013 and 0.025 for the sides and for the bed of the channel. Find the discharge passing in the channel. So what is the discharge passing through this channel? So you have equal Manning roughness on both sides, but on the bed of this channel, you have 0.025. So the channel is made of different material. So you have different roughness property. So let us see the solution, very simple. for the bed N1 given 0.025, P1 only you take 2 meter, for the side N2 this one, P2 this one. So according to Horton's formula, we will use just average subsection velocity and average velocity and average subsection velocity equals an assumption. So you have summation of Pi Ni the power of 3 over 2 the whole third over total perimeter third. So once you compute this one, you get this result. You get this result. Then 2 times this one summation over total weighted perimeter. You have 2 plus 6. So this is the equivalent roughness. So discharge will be Q equals A over N equivalent. Clear? N equivalent then times R 2/3 then radical S naught. So this is a solution. So you can arrive. Let's go to this example just as exercise. You can try as assignment compound and composite channel. You have compound channel and different roughness property. So a compound channel shown below with 6 meter wide at the top, the main channel. This is the main channel. Then 10 meter wide at the top of the flat channel and 10 meter here, 10 meter for the flat channel and the main channel 6 meter as constant bed slope for both. Bed slope is the same. Channel bed slope at this point and at this point the same. Assume the flow is steady and uniform, and the Manning coefficients do not vary along the channel, but it differs across the channel. Across the channel, the Manning roughness is varying, but along the main channel, longitudinally, just the same, no change. So you have dimension 2 meter here, 1.5. Then finally, you can just calculate. So 2 meter bed dimension. So you have concrete channel here with 0.014 and light brush for this flat channel and to 0.05. Then how do you compute? So very simple, the same. What is the equivalent Manning roughness coefficient? First, you have to compute equivalent Manning roughness for this one. So I hope so I think we can see this is the solution. You simply calculate A1 first for this one. You have to compute 0.5 times 2 plus 6, 2 plus 6, which is 8, 2 plus 6, which is 8. Then finally, you have 1.5, which is slope, just b plus my times y, which is 1.5 here you have. This is 1.5, then you can compute. If this is 2, then you have to subtract from 6. It will be 4. So you have 2 square plus 1.5 square. You can add this one. Then finally, just you can calculate. So this is half base 1 plus base 2. For this trapezoidal channel, for the bottom channel, you have 1 over 2 base 1 plus base 2 times h, which is plus 2 times 6. A1 means total area of this one. So 18 meter per meter square. For this second area, you have 2 times 10. You have 10, then 2 meter depth, 20. Total area, you have 38 meter square. Then P1, again, you have P1. P1 is just the perimeter of the main channel, concrete channel. You have 2 meter depth, this one, 2 meter depth. Then plus 2 times 1.5 square plus 2 square under radical, which is this one, the slant things, plus 2, you have plus 2, then twice, this is just added already, 2 times, then 2, then you have this result. Then once you get this result, then P2 again you can calculate. P2 is 2 meter plus 10. So this is 12 meter you have. Then total perimeter, you can sum up P1 plus P2, and hydraulic radius total you can calculate. So total using just using whole section method, already we can compute now. So first you have to compute N equivalent, which is equivalent roughness summation of Pi Ni the power of 3 over 2 the whole to third over total perimeter to third. Then we get this result. Then finally Q will be A over N equivalent. Then you can substitute every parameter, then you get this is the result, which is 66.038 meter cube per second discharge. So according to partial area method, just as assignment you can try. For each sub area, you have manning roughness, so you have to compute Q1, Q2 individually, then you sum up, then you will compare both. Okay, so second exercise is this one. Compound channel is necessary when the flow goes over the top of the trapezoidal channel as it moves to the flood plane, so that the section allows to carry more discharge. So we provide compound channel if the flood magnitude goes beyond the capacity of the main portion of the trapezoidal channel. We provide on both sides, left and right, most of the time symmetrical. We provide. Then finally, it can accommodate the incoming flood discharge. So if the flood channels are 10 meter wide, 10 meter, which is this one, 10 meter, and side slope 3 horizontal, 1 vertical, and the manning roughness coefficient, this one. For the bed, this one, you have for the bed. Then just for the sides and for the bed given, then S naught for the main canal, you have different S naught again. Be careful on this one. Then finally, you will find the discharge for a flood level of 4 meter using whole section method. And using partial, you can try. So I think these are compound channels. Now let us go to economic channel cross section. So economic cross section, if M is given, if side slope is given, how do you complete? So a slightly rock brick line this roughness trapezoidal channel carrying a discharge of 25 meter cube per second is to have a longitudinal slope of 0.004 and side slope of 1.5 to 1 vertical. Analyze the dimension of an efficient and economical trapezoidal section. So M is already given. So if M is given, already we derive equation dP by dy. dP by dy equal to 0. So after derivative, we found this area and we have bottom dimension, perimeter, etc. different equations. So you simply substitute here M. Then finally, you can find area in terms of y. So area in terms of y is this one. Then using Manning equation, you will substitute all parameters: discharge, area, Manning roughness, bed slope, etc. Let us calculate. So you substitute all given parameters in this equation, in Manning equation. The only unknown is y. So y will be 2.83. So once you know y, you can have b in terms of y. Since m is known, already we derive this equation. Then you substitute y, the calculated value of y. Then finally, bottom dimension will be 1.714 meter. So as a remark, for a given depth y, but if m is not given, we just derivate dp by dm. dp by dm equal to 0. For what value of side slope the channel will be more efficient in the economical cross section? Already we prove this one, or just it is 60 degree from the horizontal. If the side slope is 60 degree from the horizontal, we have root 3 over 3. Then after substitution in the equation of area, perimeter, bottom dimension, we found these equations for most economic cross section. If m is not given, you have to have root 3 y square, area, perimeter is 2y root 3, and the bottom dimension is p over 3, and m will be this one. So accordingly, we have just to compute like that. So this is as an example. If M is not given, for example, if discharge is given, clear water is built with concrete non-erodible channel having a slope of this one and N is this one, proportion the dimensions for most economical channel. So for most efficient and economical tropical channel section, just we have these equations already proved because we derive M root 3 over 3. Then we have area, perimeter, etc. So you just substitute in Manning equation because you have Manning equation here, bed slope and Manning roughness known, discharge known, then only unknown is y. So by try and error, y will be 2.03 and bottom dimension will be 2.3. So I think this will help you a lot. If you have any question or comment, please forward. Thank you. Okay, so this is all about today's tutorial. Hopefully you liked the video. If you have any comment or doubt regarding this topic, please let me know and write down in the comment section below. I will definitely reply on it. So please like, share this video with your friends and subscribe to my channel to get more videos on similar examples. And thanks for watching.